learners, hello grade 12s. We want to welcome you to EduBlush Virtual Academy. Thank you so much for joining us. And your presenter is Mr. Sylvester, a physical science educator. I'm going to be taking you through your whole syllabus for physical science. And this is my fifth presentation under the topic Work, Energy, and Power. And in this presentation, I am going to introduce a new concept which is very important when it comes to our syllabus, and maybe you've heard about it. It's called the work energy theorem, right? So we are going to be using the work energy theorem to do most of our calculations under this topic, work energy and power, right? There are a few things that I want to highlight before I introduce the work energy theorem. Um, Number one, I said there are three options that are at our disposal. There are three options that we can actually use to uh, calculate network done. I think I need to capture that. I need to write that so that all of us can see. So I should say there are three options, right? There are three options, right, that we can use to calculate network done. So whenever you are presented with a question where you are supposed to calculate network done, there are three options, of which the third one is the one that we are going to be looking at in this particular presentation, which is our lesson 5 under the topic work, energy, and power. So the first option that we use to calculate network done is when we add all the work done by all the forces that are acting on the object. So the first method or the first option says we add, right? We add all the work done by all the forces, right, that are acting on the object. That is option number one. So suppose we have got an object that is being pulled to the right by force applied, experiencing friction. Our network done, we are going to calculate work done by force applied. We calculate work done by friction. We calculate work done by Fg. We calculate work done by normal force. Then we add, right, all these work done, and that gives us our network done. So in other words, in science, net, it means summation. We are putting together all the work done by all the forces, though we know that all the perpendicular forces do not work. Like if an object is on the ground, our Fg is perpendicular to the ground, or so it does not work. And if we don't have any force at an angle, our Fn also does not work because it is perpendicular to the surface. And remember, in our previous presentations, we said all perpendicular forces do not work because they create an angle of 90 degrees, and cos 90 gives you a 0, and that 0 nullifies everything. So all perpendicular forces do not work, right? So the first option for calculating network done, we add all the work done by all the forces that are acting on the object. Option number 2, for calculating network done, we use Fnet, right? We calculate, right? We calculate net force, which is Fnet, and we use the formula. We use the formula. The formula now is Wnet is equals to Fnet multiplied by displacement by cos theta. That is the second option that we have that we can use for calculating network done. So how do we calculate net force? Right? This is part of vectors in grade 11. net force, we add all the forces that are parallel to motion. But as we do so, we must always remember that force is a vector quantity, therefore the direction matters. So when we calculate our F net, we look at the direction. But if the F net is positive and your positive is the direction of motion, then it means your theta there is going to be 0. So W net is equals to F net. F net, we add the forces that are parallel to motion, but taking note of the fact that force is a vector quantity. So after getting our F net, we multiply by displacement. How far did the object move? Multiply by cos theta. And I want to emphasize that your theta under cos theta, that theta is the angle between force and direction of displacement. Then you get your network done. I think we have used this method in our previous calculations, in our previous presentations. I think I can also try to source one or two questions where we can make application of this option number 2, which is actually my favorite as your teacher. I would prefer option number 2 because it's straightforward and it's easier for me. As long as the forces are given, I determine my F net and then straight away I calculate network done. And also remember, if the force applied is at an angle to the direction of motion, you must always resolve that force applied into its components, that is the vertical and the horizontal component. And then you include the component in your calculation for F net, and then you get your W net. Then option number 3, which is option number C, which is actually the theme of this presentation, which is lesson number 5. It is called the work energy theorem. So the work energy theorem. This is the third option that we can use to determine or to calculate net work done. If we are given velocity and mass of the object as it moves through displacement, then we can calculate our network done, because the theorem has proved to us that the network done is equivalent to the change in kinetic energy of the object. So the formula for the work energy theorem, actually, if you look at the term itself, the topic work energy theorem, it's a summation, it's a combination of two things: work, that gives us our network done, and then energy, right, which gives us the change in kinetic. So there are two things we are equating here. Remember, when we started the topic, I also said work done is equals to energy transferred, right? And I said when we have a positive work done, it means the object has gained energy. It has gained an equal energy, right? So if your work done is 200 joules, it means, and it's positive, right? The object has gained also 200 joules. If you get a negative work done, let's say minus 50 joules, it means the object has lost 50 joules. So work done is equals to energy transferred. So we are saying, according to the third option for calculating network done, we are saying the network done on an object, right, is equivalent to the change in the kinetic energy of the object. So by formula, W net will be equivalent to delta EK, right? Just trying to expand the formula a bit. W net is equals to, how do we calculate a change in kinetic energy? It's equals to final kinetic energy minus initial kinetic energy. Just trying to continue to expand the formula out of interest. That is equivalent. How do we calculate final kinetic energy? Half mv squared F minus half mv squared I. That will be our change in kinetic energy, which is equivalent to net work done. So in short, what I'm saying here is, learners, if you are to calculate net work done on an object, you analyze the question: what is it that you are given that will actually make your life easy? if you are given forces acting on an object, if you are given the magnitude of the forces acting on an object, then it's not debatable. It means you can either use option one or option number two. But if you are not given the forces, but you are given the velocity or the speed of the object from the point where it started to move and the velocity at the point where it ends, where your displacement ends, then it means we can't use the first two options there because the forces are not given, but I'm given velocity. So it means I can use the third option, which is actually the work energy theorem. And I equate network done with the change in kinetic energy of the object, and that's what we call the work energy theorem. Right. So in my next slide, I'm going to give you the work energy theorem, and also label the formula, and also explain few basics under the work energy theorem. It is very important for us to appreciate the work energy theorem, for we are going to use it in most of our calculations. So let's write just a few notes. Of course, I want us to start by defining the work energy theorem itself. So just write work energy theorem, right? Work energy theorem. And then we can underline our topic and then we define it. What does the work energy theorem say? It says the net work done. It says the work energy theorem in words. It says the net work done, right, on an object. The net work done on an object is equal, all right, is equal to the change, is equal to the change, is equal to the change in the object's kinetic energy. So let's say there are forces that are acting on a particular object, moving an object from point X to point Z. Now, if we are to calculate the network done by those forces, that network done by those forces on that particular object, that will be equivalent to the change in its kinetic energy. And remember, when we calculate change in kinetic energy, it's always final kinetic energy minus initial kinetic energy. So by formula, work energy theorem, it's W net is equals to delta EK. This is very, very important. So we can further expand it and say W net is equals to EKF minus EKI. W net is equals to half mv squared F minus half mv squared I. That is the work energy theorem. Now, our change in kinetic energy, I think we just need to note that mass is constant. We are still talking about the same object, but the velocity is not the same. So that's how we calculate the network done using the work energy theorem. Um, I think this is very clear, and it's very easy for us to use as well. But I also want to highlight something there before I can cite an example. Let's say the object, we can also use the work energy theorem to calculate work done by any other force. Let's say they tell you that the object was moving at a constant velocity. You must appreciate the term constant velocity. Constant velocity means velocity was not changing. So final velocity and initial velocity is the same. So it means your W net will be equivalent to zero, because if it was moving at a constant velocity, there is no change in kinetic energy. So W net will be equals to zero, and so you expand on the W net side so that you can get whatever you want to calculate. Now I'm going to do this question for you, where I am going to make an application of the work energy theorem and try and explain how it works. Maybe I need to label this formula before I move on to the next slide, where W net in this formula, it represents the net work done. And remember, we said work done is equivalent to energy transferred, right? So it is also measured in joules. And then your EKF represents your final kinetic energy, right? And all forms of energy measured in joules. And then EKI represent your initial kinetic energy, right? You remember in grade 10 how you calculate kinetic energy. Kinetic energy is half mv squared, right? So the difference between EKF and EKI is that for final kinetic energy, we use the final velocity. For initial kinetic energy, we use the initial velocity, and then the rest follows. And maybe you need to appreciate your mass there. M represent the mass, right? And your mass is supposed to be in kilograms, and your velocity is supposed to be in meters per second. So maybe I need to capture that as NB. That is, you calculate your kinetic energy, your mass, right? M represent mass, and your mass is supposed to be in kilograms, and V represent, maybe VF represent final velocity, which is measured in meters per second, and VI represent initial velocity, which is measured also in meters per second. So take note that when you calculate using these formulas, your mass is always supposed to be in kilograms, and your velocity is supposed to be in meters per second, so that you don't have a confusion when it comes to the calculation. So in our next slide, I'm going to do an example for you, and I use the work energy theorem to calculate whatever that I'm supposed to calculate. Um, okay, so suppose we have the following. That's an example now that I'm doing under the work energy theorem. I'm going to draw a diagram and write few questions, and then I calculate everything for you. So just sit back and listen very carefully so that we don't lose each other. So in our example, a worker pulls a crate, right? Uh, okay, we need that. A worker pulls a crate. I think we need that story. A worker, right, pulls a crate. This is very important for us. Pulls a crate uh, with a mass of 30 kg from rest. By applying a force of 50 newtons. By applying a force of 50 newtons and experiencing frictional force of 30 newtons and experiencing, right, experiencing a frictional force, a constant, right, a constant frictional force of 30 newtons. So the crate experiences a constant frictional force of 30 newtons. So the diagram, we need the diagram quickly here. So we are having our ground here. I'm going to draw a very small diagram because of space. So we have the crate, which is slightly big, and this crate, they said, is 30 kilograms. It is pulled right by a force of 50 newtons, right? And it moved through a distance of 6 meters. And as it was moving, it experienced a constant frictional force of 30 newtons. So that's it. So this is point O and this is point P. Now let's go to the questions. Item A, it says draw a free body diagram and indicate all the forces. So the first question is a free body diagram. And we know that in our free body diagram, unless stated otherwise, we must state all the forces. The second question, it says calculate the network done on the crate. Calculate the network done. Calculate the network done on the crate. Right, as it moves from point O to point P. And then item number C, it says use the work energy theorem. Use the work energy theorem. So as long as we are guided like this, we can't use any other option. Otherwise, we get a zero. So use the work energy theorem to calculate the velocity, to calculate the velocity or the speed of the crate at point P, the velocity of the crate at point P. Right. Allow me, friends, to divide the page into two so that my calculation can fit very well. Uh, I'm going to divide this into two so that my calculation can fit properly. Good. Okay. So I have to read the question 3 times so that I can appreciate what's happening in this particular scenario. So a worker pulls a crate with a mass of 30 kg from rest. I think we need to underline the term rest there. When something is at rest, it means it's not moving. So its velocity is 0 meters per second. By applying a force of 50 newtons and experiencing a constant frictional force of 30 newtons. Maybe I need to make a quick comment on frictional force. Frictional force always opposes motion. That is very important for us to remember. All right, so that's the diagram. So we have a displacement of 6 meters as the object or the crate moves from point O to point P. Question number A, it says, draw a free body diagram. This one is simple. I'm going to put a dot which represents the crate, and then I have got my force applied, right? So this is force applied. Then I have got the weight of the object, or just write FG. And then since the crate is in touch with the ground or is in touch with the surface, there is a force that the surface exerts on the crate, and it's a contact force. It only exists when the object is in touch with the surface, and that force is always perpendicular to the surface, and it is known as normal force. So make sure that when you indicate your Fn, it creates 90 degrees, right? And then obviously they said something about friction, and friction opposes motion. So that is kinetic friction because the object is in motion. So that's it. That's how I draw the free body diagram. There is no force that is at an angle that I can resolve into components. So that represents my free body diagram. Then I move on to item number B quickly. Calculate the network done on the crate. Remember, friends, we can't use option number 3 because we are yet to use it to calculate velocity at point P. But if we had velocity at point O and velocity at point P, the work energy theorem was going to be the easiest to use to calculate network done. So in this case, It means we can use either of the first two options, right? We can use the first option, which says add all the work done by all the forces that are acting on the object. So we know, friends, listen very carefully here. We know that Fn and Fg, they are perpendicular to the surface. In this case, they do no work because they are perpendicular. They are theta, angle theta. The angle between force and direction of displacement is 90, and cos 90 gives us 0. So it means the only work done that we are going to calculate here, it will be work done by force applied plus work done by friction, and that gives us our net work done, right? But like I said, I prefer that I use the second option, which is the FNet method, right? Good. So I'm going to use the second option, which says WNet is equals to FNet by displacement by cos theta. So I have to calculate my FNet, but I've got only two forces which are parallel to motion here, force applied and friction. And I'm going to take the direction of motion as positive, which means my force applied is what? Is positive, right? So any force that is going to the right, positive, so that any force that is going to the left becomes what? Negative. So as I calculate my Fnet, I'm going to take my right, which is the direction of motion, as positive, so that left becomes negative, right? So WNet, I'm going to substitute right inside the formula. So my Fnet will be equivalent to force applied. It's positive because it's going to the right. Plus, Fnet, remember we are summing up. Plus minus Fk. It's minus Fk because it's going to the left. So this represents Fnet. Then by displacement, how far did it move, which is 6 meters, multiplied by cos theta. So if my Fnet is positive, it means Fnet is going to the right and the object is going to the right and your theta is 0. Right. So Wnet, let's expand together. What is our force applied? I'm sure it's given somewhere. 50 newtons minus our Fk is given somewhere is 30. So 50 minus 30, I get a positive 20, which means the direction of Fnet is to the right and the object is going to the right. So our theta is going to be 0. So this is times displacement, 6 meters, times cos. Now, what is our theta? It's 0 degrees. Why is 0? Because I'm getting a positive Fnet here, and positive, the direction is to the right, and this crate is going to the right. So Fnet and the crate, they are going in the same direction. So our theta is 0. So I need a calculator there. Wnet is equals to 50 minus 30, I get 20 times 6 times cos 0 degrees. Therefore, Wnet, remember, we measure everything in joules. So we need our calculator there. Let's use our calculator to calculate that. Of course, cos 0 is 1, so it's 20 times 6, which is 120 times cos 0, which is 1. It remains as 120 joules. So this is the net work done. Simple and straightforward. So uh, if we are to use, so WNet is 120 joules. I hope you can see clearly there. I pray that you can see there. If you use your calculator, you can see that is 120 joules. Please take note of that. Now, what if I use the first option to calculate net work done? I calculate work done by force applied plus work done by friction. So that's option number 2. So this was option 1, right? So you guys, you choose the one that is easier for you. Allow me to use also option number 2, where I'm going to say WNet, which is net work done, is equals to work done by force applied plus work done by friction, right? So W net, I'm going to expand everything there. How do we calculate work done by force applied? It's equals to force applied by displacement by cos theta plus work done by friction is friction times displacement times cos theta. Right. Good. So W net is equals to our force applied is 50 times displacement 6 times cos. Who is our theta for force applied? Force applied is going to the right, learners, and the object is going to the right. So force applied and motion, it's in the same direction. So your theta is 0. So this whole expansion represent work done by force applied. Plus, our frictional force is given is 30 times displacement, which is 6 times cos. What is our theta? Remember, theta is always the angle between force and direction of motion. Now, when you look at the free body diagram, you can appreciate our theta better there, right? Because our FK is going to the left and the object is going to the right. So your theta, look at the free body diagram. I'm indicating your theta there. So your theta is going to be that angle, which is actually 180 degrees. And cos 180 is minus 1, which means friction is doing negative work. Yes, it should do negative work because it's going in the opposite direction. So W net is equals to what is work done by force applied? That's 50 times 6. I'm getting 300, right? So that's 300. Obviously, I'm going to get a negative because cos 180 is minus 1. So it's 30 times 6. That gives me minus 180, right? So therefore, W net is equals to 300 minus 180. I'm getting 120 joules. I'm getting the same answer. So it's up to you now. You choose, you decide which option do you want to use to calculate W net. All right. Without wasting much of your time, let's move on to item number C, which is actually the purpose of the presentation. Use the work energy theorem to calculate the velocity of the crate at point P. Now, when the question is so specific, so particular, use the work energy theorem. We are guided. It's not an open question. We don't decide. They've already decided for us. It's either we use the work energy theorem or we use the work energy theorem. Otherwise, if we use any other method, then it means everything is going to be wrong. So the first thing we need to state our work energy theorem. And before you use it, normally in exam, they request you to state the work energy theorem in words. So you must know it, the work energy theorem, which says the net work done on an object is equal to the change in the object's kinetic energy, right? So let me write the work energy theorem, which says W net is equals to delta EK, right? So my network done, I've already calculated it. So I need to substitute because of time and because of space. So my W net, I got 120, which is equals to half times the mass of the object is 30 times VF. That is the velocity of the block or the crate at point P. That's what I am looking for. Minus initial kinetic energy, which is half times 30 times. What was our, remember this is VF squared, right? What was our initial or the speed of the created point O? It was moved or pulled from rest, which means our initial velocity is 0 squared. So 120 is equals to half of 30, that's 15 VF squared, minus, that gives us a 0, right? So what am I having here? I'm going to have 120 is equals to 15 VF squared. Divide both the sides by 15. Divide both the sides by 15. So VF squared is equals to 120 divided by 15, which is 8, right? And then square both the sides. We are doing math now. Therefore, VF is going to be the square root of 8. What is that? What are we getting there, Lenas? I'm getting 2,83. 2,83. We round off our answers to two decimal places, meters per second. Then you underline. That is the speed of the crate at point P. So, ladies and gentlemen, friends, learners, grade 12, this is how we use the work energy theorem. This is what work energy theorem says to us. So tomorrow they might not ask you to calculate speed at point P. They will ask you to calculate speed at point O. So in other words, you are going to be looking for VI. Let's say it was not pulled from rest. So you are going to be looking for VI. So it's just a matter of substitution, and then the next thing we get our answer. So thank you so much for joining us. Please continue to follow our lessons, our presentation. This was lesson number 5, this presentation. I'm going to be presenting lesson number 6 again, where I'm going to be doing more questions on the work energy theorem. Thank you so much. Edge Blush loves you.